Welcome back, class. In today's class, I want to focus on what's called the ideal gas law. So, this is an equation that we can use to understand gas behavior by combining the three simple relationships that we just looked at, right? So, if we take the relationships of volume being inversely proportional to pressure, being directly proportional to temperature, Charles' law, and directly proportional to moles, Avogadro's law, and we combine them, we get that volume is proportional to the moles times the Kelvin temperature divided by the pressure. Now, to convert this proportionality into an equation, we insert a constant, and that constant here, right, is R. And with a little rearranging, we get what we call the ideal gas law, which is P times V equals N times this constant times T, right? And of course the order doesn't matter here. This is just the typical order that you see it expressed in. So R here, right? What is R? Well, R is a proportionality constant, right? And we saw that when we talked about the simple relationships, right? To turn these into equalities, right? To show that linear relationship, right? We had to introduce a constant, right? And we called it R. Now, what does that value equal? Well, it equals, in our case, the most common version of R that we use is 0.08206 liters atmospheres per mole Kelvin. Now, you will find other versions of R that have different units here, right? Different volume units, different pressure units, right? But this is the one that we will use when we do these gas law calculations. Now, what this tells me is that when I use the ideal gas law, I am restricted to my units, right? The volume must be in liters, the pressure must be in atmospheres, and the temperature must be in Kelvin, and of course N is in moles always. And so if we're doing problems that have different units of that and we're using the ideal gas law, we have to convert to those units. Okay, so here's the idea, here's our ideal gas law. Now, this law is especially useful, and where we see it used is to look at a situation and calculate a missing variable. So, remember the base equation here, PV equals nRT. And so, this equation is good when I know 3 out of my 4 variables, right? So I have pressure, volume, moles, and temperature. And if I know 3 out of those 4, I can use the ideal gas law to calculate the missing one. So let's jump right into a practice. So a car tire has a volume of 10.0 liters, contains 0.721 moles of gas at 345 Kelvin. And we want to know what the pressure is in atmospheres. Okay, so let's see what we know. So I like to just list our values here. So pressure here is 0.721 atm. Volume is 10.0 liter. N is equal to, read this correctly. The pressure is unknown, right? That's what we're trying to find. the volume is 10 liters. The moles are 0.721. And the temperature, 345 Kelvin. Okay, so let's start into our equation. So, pressure, oops, let's use a different color. Pressure, if we rearrange our equation, right, move volume to the other side, equals nRT over V. So now we can plug in our numbers. So our N here is 0.721 moles. Our R number is 0.08206 liter atmosphere mole Kelvin, and 345 Kelvin divided by V, 10.0 liters. So if I check my dimensional analysis, I check my units, I see that moles cancels here by 1 over moles. I see that Kelvin cancels with the 1 over Kelvin here. And I see that liters cancels out with liters here on the bottom. So I'm left with ATM, which is what I should have. So if I do my math, my pressure comes up to 3 significant figures as 2.04 ATM as the pressure in this situation. Okay, that's the ideal gas law, right? It's good for calculating a missing variable when we know the other 3. So let's try one more example here. This one, we want to know how many moles and the volume, 250.0 milliliter container at a pressure of 680 millimeters of mercury, 25.0 degrees Celsius. Now, what I quickly can look at here and see is my units, right? So I see that my volume is in milliliters, but I need that to be in liters. My pressure is in millimeters of mercury. I need it to be in atmospheres. My temperature is in Celsius. I need it to be in Kelvin. So I have to convert these. So let's start with the units conversions here. So I got 680 millimeters of mercury. Now I want to go to ATM, so I know that I'm going to have ATM at the top, millimeters of mercury at the bottom, and my conversion is 1 ATM equals 760 millimeters of mercury, and this equals 0.895 ATM. Right, millimeters of mercury cancel. So my pressure here equals 0.895 ATM. Do my volume, got 250.0 milliliters, and I need to turn that into liters. So my conversion between milliliters and liters is that 1 milliliter was 1 times 10 to the minus 3 liters. So if I do my calculation, I get 0.2500 liters. Milliliters cancel out. So volume here, 0.2500 liters. And then finally my temperature. My Kelvin temperature equals my Celsius temperature plus 273.15 equals 298.15 Kelvin. And of course N, in this case, is what we're trying to find. Okay, so now that I have all the right numbers and all the right units, let's do the math. So if I rearrange for N, so that means I'm going to divide both sides by RT. I get N equals PV over RT. Which equals 0.895 ATM times 0.2500 liters divided by 0.08206 liter atmospheres mole Kelvin and 298.15 Kelvin. Of course, I follow my units. I have atmospheres here and atmospheres on top here. I have liters up here, liters down here. I have Kelvin and division by Kelvin, and that leaves me with moles. Now, it could be kind of tricky, but what this, if you really were to look at that, what that is 1 divided by 1 over moles, right, which really equals moles, right? So yes, if I do all this, the units will come out as moles. So I do my math, and my moles equals 0.00915 moles, or 9.15 times 10 to the negative third moles. 3 significant figures, right, based on the other values that we have in our equation. Okay, so that concludes my discussion of the ideal gas law. Next time, we're going to work on some more calculations.